I mean, this is the way it is. This is how science is. And yes, it is a theory.
And I must say that my sympathy goes out to you who are science teachers who are on the front lines, because America does have this peculiar history of resistance to evolution, because William Jennings Bryan, who was very much of a, not just a liberal, he was a progressive in so many other ways, latched onto this issue, and it's become part of a peculiarly, not entirely uniquely, but peculiarly American problem. But my analogy, and I say this all the time, is that you could no more study biology or make progress in biology without it believing in the theory of evolution than you could build an airplane without believing in the theory of gravity. And yes, gravity is just a theory, but if you put a rock over my head, I'm pretty much going to believe it's going to drop on my head, and evolution isn't much different from that. And what do you?
That's right. Yeah, it's absolutely true. I mean, it's a simple concept. It's the unifying principle of biology. It's got to be taught.
It was really fascinating today to hear these talks from these two eminent scientists about what everybody wants from the reason that the public supports science, which Mary Lasker understood very well, is that people want drugs to cure diseases and they want to live a better life. And their talks had nothing to do with paleontology or apes or anything else. It had to do with chemicals in the laboratory. And yet evolution is the driver of both your talks. And I think that there is this strange disconnect. So we're going to call on some students now, beginning with a Lily McBee, who I happen to know works for one of the scientists on this stage.
So I had a question about how you start off research, and here it goes. After starting with a monumental question, such as how did the first living organisms arise on Earth, how do you single out a specific aspect of that question that you can translate into a series of experiments?
Yeah, well, that's a great question. So the origin of life is such, I mean, it's a big problem, right? With lots of parts. I mean, there's this sort of continuum all the way from, I love talking about parts of it with astronomers or planetary scientists or chemists. So you have to focus in on one aspect, and the aspect that we chose to focus in on is just the origin of cells. And then, so it's partly a matter of sort of reductionism, breaking a complicated problem down into simpler parts that you can address. So you have to find experiments that can answer specific questions. And so we take the problem apart into membranes and nucleic acids, and then in terms of membranes, you got divided into growth and then division. So you sort of narrow, simplify things and start addressing those simpler questions, and then you sort of reverse the process and try to figure out how things get put back together. So that's how I think about it. But it's really important to break it down to experimentally tractable problems, right? Because there are lots of interesting questions that are completely intractable, and there's no point working on them right now. So you have to find questions that can be technically addressable.
Well, let me, Jack, follow up with that Lily's question with your own personal trajectory, because you started out and you won the Lasker and the Nobel for this work on chromosomes. Did that naturally lead you to this study of the origins of life, or was it your success in that enabled you to have the freedom to ask this other question that may not lead to a specific application so quickly?
So I've kind of bounced around in different areas. I don't think there was a direct, continuous path. In fact, after working on problems of chromosomes and DNA repair and stuff like that for years, I consciously wanted to do something else. And the reason was that I felt that those fields were getting very crowded. Experiments that we thought of were being done by lots of other labs. So to me, it's not very much fun if you know, what you're doing is going to be done anyway by someone else. You might as well go and find a more interesting problem. So, you know, I thought about going into neurosciences, but that was too hard. Thought about, I don't know, several different fields. But Tom Chick's work on ribozymes was very new and exciting, and I thought there were a lot of interesting questions. And it was close enough technically that we could do it. So that sort of led to that transition.
And Brian, you're at a different place entirely now because you're younger, with all due respect. But you are following some very specific leads that started out as a graduate student and as a postdoc, and now you're an assistant professor. But it's not like you have the luxury of thinking, oh, what am I going to work on next, right?
No. Very specific interests. You know, smaller operations, smaller number of people. I mean, we have to think about very next step things that we can demonstrate. You know, that we have these technical capabilities. We don't have my laboratory does not have this track record of capabilities, and so this is something that factors into my considerations. Although the work that we talked about, or that I talked about at the end of my talk, is brand new, and I don't know where that will go, and I don't even know exactly how plausible it is. But it was definitely a departure from anywhere I have been previously.
So next question, two people composed some questions together, so I want to see how this works. KJ Longhurst and Lena Leone. Go ahead.
Right, so from different high schools, we're at different levels. We have some seniors this year. Lena and I are juniors this year. But as juniors, we're looking into colleges and more things that we can get involved in later. And as an undergraduate, you said, Mr. Pagel, that you were involved in, what exactly were you thinking in terms of?
That's a good question.
What were you thinking? Why did you get into the sciences?
That's a very good question. What was I thinking?
All right, so what exactly were you thinking in terms of extracurriculars, maybe, that how you, how else did you get involved in the sciences? Were there internships like we have now, and what other opportunities were you given? Also for Mr. Shostak.
Extracurricular activities. I've actually, when I was a high school student and an undergrad, I always figured that I was a very well-rounded person. And so, especially when I was an undergraduate, I volunteered in a lab, actually. Then in my second year, became an independent researcher there in ultra-fast laser spectroscopy. Had nothing to do with what I do now. Just because I wanted to get in there and I wanted to work for a professor who would allow me to actually do research and not clean glassware. And so that really kind of solidified my interest, because I loved working in the dark and futzing with these lasers and mirrors. It was fantastic. Outside of that, I studied Japanese and I played in the orchestra. I mean, it was just completely unrelated. I mean, it wasn't that I was in the lab at all hours of the day and night. That came in graduate school. That was later. Whereupon I no longer spoke Japanese or played in the orchestra. I was a piccoloist.
Did you want to give some?
I probably was not nearly as well-rounded as you were. I guess somewhat more focused, but also, I did summer jobs in labs. Got into labs as quickly as I could, and really liked it, and just kept doing that.
Great, thank you.
Lena, did you have a question? Please.
Well, I wanted to know if there are any specific people that you would say have inspired you or have been your mentor, and who are they, and how have they guided you in the path that you have chosen?
Well, I've had, really good teachers and mentors all along the way. So there were a couple of teachers in high school who are really inspiring and, made biology or science seem really interesting.